Welcome to the 30th lecture of combinatorics. In the last class, we had started discussing the technique of solving recurrence relations using generating functions. So, we start with an example. So, this is the example we are considering. Solve the recurrence relation Hn equal to 5 times Hn minus 1 minus 6 times Hn minus 2, n greater than equal to 2, right. So, this recurrence relation is valid only for n greater than equal to 2, because you need Hn minus 1 and Hn minus 2. So, that means H1 and H0 should be given. So, here the initial values H0 equal to 1 and H1 equal to minus 2 are given. Now, how do we solve this thing? To solve this thing, so this is what Hn equal to 5 Hn minus 1 minus 6 Hn minus 2. So, I will write the initial values here, H0 equal to 1 and H1 equal to minus 2. So, note that the sequence will be like H0, H1, H2, H3 and so on, which is this is 1, this is minus 2, and what is H2? H2 will be you substitute that will be 5 into minus 2, that is minus 10 minus 6 into 1, 6 into 1, right, minus 10 minus 6, that is it will be minus 16 and so on, it will go, right. So, we know that our generating function, say if I write g of x as the generating function for this will be 1 minus 2x minus 16x square and so on, right. So, this is, so we want to find a closed form for gx first. If you remember, this is what we are trying to do initially, and then once you get the closed form, then we will try to get a general closed form expression for the coefficient of x raised to n in it. So, that will be the value of Hn, right, because the generating function gx is actually H0 plus H1 x plus like that Hn x raised to n plus this. So, if you find the, so you first find a closed form for gx somehow, and then from that infer somehow what would be the coefficient of x raised to n, that would correspond, that should be Hn, right, that should be the value of Hn. This was our method, right. Now, right, this is what we want to do, right. So, how will we find out for this? Earlier we had find some examples where we could infer the coefficient of x to the power n given some closed form expression for g of x. Now, first our task is to first get g of x, right. So, here we write like this first g of x. So, we start like this, so first let us write this in a this formula Hn equal to 5 Hn minus 6 Hn minus 2 in a more convenient form. So, Hn minus 5 Hn minus 1 plus 6 Hn minus 2 equal to 0. This is the way we started off when we wanted to find the characteristic equation also, right. So, this is the underlying recurrence relation, right, this captured by this relation between Hn minus 1 and Hn minus 2. Now, what I write is, let g of x equal to H0 plus h1 x plus h2 x square plus h3 x cube plus so on. Now multiply g of x by minus 5, this is the coefficient of hn minus 1 here, into x. That means minus 5 into x times g of x. What will be that? It will be, see, h0 into minus 5x, h1 into minus 5x into x, that means minus 5 h1 into x square and so on. But when we write it, because you know h0 into minus 5x, so that has already got an x, so in this, the expansion of this, there won't be any constant term. Therefore we will start writing from here. So this is minus 5 into h0, right, into x, this is the first one, and then minus, sorry, here minus 5 into h2, sorry, h1, so this one, right, h1 into x square. So I multiply h1x into minus 5x, minus 5 into h1 into x square, and then again minus 5 into h2 into x cube and so on. This is what we will get, right. So next what we do is to multiply gx by 6x square. We multiply by 6x square this gx. So you know that there won't be any constant term in the resulting expression. So there won't be any term like something into x, right, no power of x will be there. So it will start with x square onwards, right. So this is, so therefore we will write it here, h6 h0 x square, that is the beginning, plus 6 h1 x cube and so on, we can write like this, right. Now what I do is I sum up all these things together. So that means I add this plus this plus, so like this. So what do I get here? I get gx into 1 minus 5x plus 6x square. That's what I will get. This is equal to, so here this will come here, h0 plus h1 minus 5h0 into x. This and this I added here and put it here, put here, and then now h2 x square plus minus 5 h1 x square plus 6 h0 x square. So if you take x square out, that is h2 minus 5 h1 plus 6 h0 into x square. But you know from n equal to 2 onwards, this for n greater than or equal to 2, this is valid, this relation is valid, this equation is valid. So put n equal to 2, what does it say? h2 minus 5 hn1 sorry h1 plus 6 h0 equal to 0. So that is exactly this one, h2 here, if you read it out like this, h2 minus 5 h1 plus 6 h0, right, into x square, but that is actually 0. When I put 2 for this, this will become 1, this will become 0, right, that is h2 minus 5 h1 plus 6 h0 equal to 0. So this will become 0, right. So there will be 0 x square only here, plus here what is happening when I take this thing into x cube is what I will get here, x cube x cube x cube here. So h3 minus 5 h2 plus h3, this is exactly see, for instance, if I put n equal to 3, this n minus 1 will become 2 and this will become 1, right. So, that is H3 minus 5H2 plus 6H1 equal to 0. That is exactly this, right, H3 minus 5H2 plus 6H1, that is equal to 0. Therefore, we have 0 x cube, and you can guess. So, from now onwards everything will be like this. If I collect the coefficients of x raised to 4 from here, here, here and here and add them up, they will become 0. And one should not be surprised why this is happening, because that is the way we have arranged, right. So, for instance, we were multiplying by 5x here, so that minus 5x, so that we pushed it one side. So, for instance, for an hn term here, hn x raised to n will be here. So, then what will be just below that, right, that will be hn minus 1 into this minus 5, right. So, that is exactly hn minus 1 into minus 5 here, right. And what will be below, because we multiply by 6x square here. So, it was pushed 2 steps towards the right. So, in the column of x raised to n, we will see hn minus 2 into the 6, the 6 came from here, right. So, 6x minus 2, right. So, into x raised to n. So, if you collect all the coefficients of x raised to n from here, here, here and here, from each of this equation column wise, then what will you see, hn minus 5 hn minus 1 plus 6 hn minus 2, right, in general. So, that will always be 0. So, from now onwards there will not be anything. So, in this sum only this portion will contribute, as you can see, right, this portion, that is h0 plus h1 minus 5h0 times x. And luckily we know the values of h0 and h1. h0 is what, that is 1, and this is what, this was minus 2. So, you have to put minus 2 for this, and this is 1, right, h0 is 1. So, that is minus 7. So, we get gx into 1 minus 5x plus 6x square is equal to, what do we get, 1 minus 7x, 1 minus 7x, this is what we get. So, what is gx? Gx equal to 1 minus 7x by 1 minus 5x plus 6x square, this is what, right. Now, we will, so this is the general expression for the generating function for that sequence given to us, h0, h1, h2, satisfying the relation, the equation hn minus 5 hn minus 1 plus 6 hn minus 2 equal to 0. Not only that, with the initial values 1 for h0 and minus 2 for h1. These are also incorporated here, because after using that only we derived this formula. In the end we substituted the values for h0 and h1, right. So, this already considered the initial values, right, and also this relation. This is what allowed us to cancel off most of the terms in the sum, right, the terms which comes after the third term, right. So, sorry, after the second term, from third term onwards we have no contribution because of this relation only, right. So, I can see that is how we adjusted things, and then so we see that this is a generating function. Now, if this is the generating function, we can discuss how we can get the coefficient of x raised to n. So, finally giving a closed expression for hn, right. So, 1 minus 7x by 1 minus 5x plus 6x square, 1 minus 5x plus 6x square. So, what we do is we to get the answer for that we have to simplify it. We use a method called the method of partial fractions. So, first notice that this 1 minus 5x plus 6x square can be factorized to 1 minus 2x into 1 minus 3x. This is not very difficult to come up with, right? So 1 minus 2x into 1 minus 3x is this. Now we can say that, so for some constant c1 and c2, so we can say that this c1 by 1 minus 2x plus c2 by 1 minus 3x. So then what we do is, we can compare the numerator now. So that means 1 minus 7x is equal to, so this will multiply here and this will multiply here. So that is c1 times 1 minus 3x plus c2 times 1 minus 2x. Right. So this is c1 plus c2 plus, so we have minus 3c1 here, x minus 2c2 x minus 2c2x, minus 3c1 and minus 2c2x. So we can compare the constant terms here and here, that is c1 plus c2 has to be 1, c1 plus c2 has to be 1, and minus 3c1 minus 2c2 minus 3c1 minus 2c2 has to be equal to this one, right? 7 minus 7, sorry, not this one, so it should be minus 7, right? Now we can solve this simultaneous equation. So this is, you can do it easily. We will get c1 equal to 5 and c2 equal to minus 4, right? Now you substitute in this equation, this is what, c1 is equal to 5 and c2 will be equal to minus 4, right? So you can put it as minus 4. This will be then the partial fraction. So by using the method of partial fractions, we can say that this 1 minus 7x by 1 minus 5x plus 6x square is equal to 5 by 1 minus 2x minus 4 by 1 minus 3x, right? So okay, so now what we have to do is, so we, from this thing, so we know this is our generating function, 5 by 1 minus 2x and minus 4 by 1 minus 3x. 5 by 1 minus 2x minus 4 by 1 minus 3x. So this is easy to handle, because this 5 by 2x, you know, 1 minus 2x expands as 1 by 1 minus 2x. What is this? This, you know, this is sigma k equal to 0 to infinity, right? Minus 1 choose k, because this is what, so we can write it as 1 minus 2x to the power minus 1, right? So minus 1 choose k into minus 2x to the power k. This is what, so the right. And then if you want 5 times this, so there will be 5 here, there will be 5 here, right? So similarly for the other thing, so this we can simplify. Of course, we know this is 5 into this minus 1 choose k, if you remember, that is just 1 and a minus 1 raised to k. This will just become k equal to 0 to infinity, right? So the 0 to infinity 2 to the power k into x raised to k, right? 2 to the power k into x raised to k. So the coefficient of, so if I am seeking the coefficient of x raised to n in this thing, that is 5 into 2 to the power n. So, coefficient of x raised to n in that will be 5 into 2 to the power n. Now, the other term, so the minus 4 by 1 minus 3x, that will also similar, minus 4 by 1 minus 3x will be sigma k equal to 0 to infinity. Same way, so that will be minus 4 here, this minus 4, and we will have 3 to the power k into x to the power k. So, the coefficient of x raised to n, if you look, that will become, the coefficient of x raised to n here will be minus 4 into 3 to the power n. So, the finally when you sum up both, the coefficient of x raised to n will be 5 2 raised to n minus 4 into 3 raised to n. So, 5 into 2 raised to n minus 4 into 3 raised to n. This will be the coefficient of x raised to n. This will be the coefficient of x raised to n. This is the way we can solve it completely. So, let me repeat. So, the first step was to somehow get that g of x. And after getting the g of x, what we did is to use the method of partial fractions to split it into more convenient terms, and then each of those terms were familiar to us. We know the expansion of that, and then from that we collected the coefficient of x raised to n from each term and then added them together. This is what we did, right. Now, when we look at this method, we will see that this is quite general, right. We can do it for any homogeneous linear recurrence relation with constant coefficients, as long as, so it's an order k, suppose. So, we can do it. So, we will just sketch out how we go about doing it, right. So, generalizing the method to solve any linear homogeneous recurrence relation of order k with constant coefficients. The associated generating function will be of the form some p of x by q of x, where p of x is a polynomial of degree strictly less than k, because this k is the order we are talking about, and then q of x is a polynomial of degree k having constant term equal to 1. So, this is the way we do. If the sequence is h0, h1, h2, etc., satisfying, see, hn plus a1 times hn minus 1 plus a2 times hn minus 2 plus, say, ak times hn minus k is equal to 0, right. Then qx will be equal to 1 plus a1 times x plus a2 times x square plus ak times x k. So, if this is easy, if you have carefully looked at what we did in the last in the this thing, so last time. So, let us say this is the recurrence relation hn minus, sorry, hn plus a1 times hn minus 1 plus a2 times hn minus 2 plus, so, a k times hn minus k equal to 0. This is our recurrence relation, right. Is equal to 0. This is a kth order recurrence relation. Now, this will be true for n greater than equal to k. Maybe this will be valid for n greater than equal to k only, because we are using h0, h1. So, for when n equal to k, we are already using all the h0 to hk minus 1, right. So, if you try to apply it for hk minus 1, we will not be able to find h minus 1, that is not available. So, our initial values will be h0, so will be given h0 equal to something, say h1 equal to something, so hk minus 1 equal to something. This many initial values have to be given, right, because this will work only from n equal to k onwards, right. Now, so if you remember, the method was that, So, the method was that, so we wrote g of x equal to h0 plus h1 x plus h2 x square plus and so on. Here we have h k x raised to k and so on. Now, first we will multiply by a1 x into g of x, right. This is a1 x will multiply g of x, and when we write we will just skip this portion and we will start here, because every term now will have an x, right. So, we will write a1 h1 times x here, and a1 h2, sorry, this is h0, this is a1 h1 times x square and so on. This will, so this here what will be this a1 h k minus 1 x k, like this, because one term we have pushed one step here, right. So, x raised to k will get h k minus 1, but a multiplier of a1 is here, right. The next we will use a2 times x square to multiply g of x, right. This will be pushed 2 steps. So, we will start from here onwards. Why? Because every term will have an x square now. So, we will start just below the x square term here. So, this will be a2 times h0 x square plus, so when we reach here what will we get, a2 times h k minus 2 x raised to k will be here, right. So, like that we can write finally a k times x raised to k can multiply g of x here in the end, after so each of so after a2x we will take a3 times x cube, then we will take a4 times a4 x raised to 4 and so on. Finally, ak times x raised to k will multiply g of x. This will directly start here, right, because x raised to k term here only it will start. So, that is ak times h 0 x raised to k. So, now when you sum up these things, right, you will get g of x into 1 plus a1 x plus a2 x square plus a3 x cube plus finally ak x cube. So, this is what here what you get is gx into 1 plus a1 x plus, so a2 x square plus and ak x raised to k. This is what we will get here. This will be equal to what? So, here when you sum only h0 will come, right, and then here when you sum h1 plus a1 times h0 into x will come and so on up to where? Up to here hk plus a1 times hk minus 1 plus a2 times hk minus 2 plus ak times h0 up to here, right. So, this essentially when you put n equal to k here, so this will become k, this will become k minus 1, this will become k minus 2 and so on, this will become 0, right. So, therefore, this will turn out to be 0, this will turn out to be 0, this is 0 into x raised to k. From here for put n equal to k plus 1 we will get, see when you sum this up this will become 0 and x raised to k plus 1, 0 into x raised to k plus 1 will go away. So, this entire thing will go away, right, only we will have contribution from only this portion, right. So, how will it look like? This will look like h0 plus h1 plus a1 times h0 times x, h1 plus a1 into h0 times x, and x square's coefficient will be h2 plus a1 times h1 plus a2 times h0 and so on, right. So, this will be the, and finally, just before the coefficient of x raised to k minus 1, right, that is h k minus 1 plus a1 times h k minus 2 plus a2 times h k minus 3 and so on. So, this is the way it will look like. Finally, a k minus 1 times h0 will be there, right. So, that only up to x raised to k minus 1 will come, right. So, this portion will be our p of x, and because g of x into something is equal to something, right. So, this will look like g of x into say some q of x is equal to a p of x. The properties of this q of x is that it has this constant term 1, because here we have always 1, right, this into g of x into 1, and then this x raised to k, that is it is a k degree polynomial, because a k is always, this is non-zero, right, that is by definition of the order of the recurrent solution is k, therefore, this a k has to be non-zero. So, this will be there. So, a k raised to x raised to k will be there. So, therefore, this is a kth degree polynomial, and the first constant term is 1 here, right, that is the property of this q of x, and this p of x is just h0 plus this thing sum, but it is only up to x raised to k minus 1, right. The degree of p of x will be strictly less than k, right. We are not saying k minus 1, it will be strictly less than k. So, g of x will be equal to p of x by q of x, p of x by q of x, right. Now, I can, for clarity, I can show the q of x and p of x here. So, q of x will look like this, q of x equal to 1 plus a1 x, this a1 is directly coming from this, and right, and this a2 x square, that a2 is directly coming from here, and then a k x square, this is coming from here. And similarly, our p of x will be h0 plus h1 plus a1 h0 plus h2 plus a1 h1 plus a2 times h0. And finally, hk minus 1 plus a1 hk minus 2 plus ak minus 1 h0, ak minus 1 h0, right, into x raised to k. So, this is what, it is very easy. So, you do not have to memorize it, you just can work out it whenever you want. You can again redo this thing, and the procedure is very easy to remember once you understand it. So, therefore, you can always do it when you want, right. You do not have to keep these formulas in mind, right. Now, let us look at one example, hn plus hn minus 1 minus 16 hn minus 2 plus 20 hn minus 3 equal to 0. So, hn plus hn minus 1 minus 16 hn minus 2 plus 20 hn minus 3 equal to 0. So, we need the initial values for, so this will work only from n greater than equal to 3, right. So, we want what is h0, what is h1 and what is h2. So, what is h0? Let us take it as 0, and h1 let us take as 1, and let us take h2 as minus 1, right. These are the initial values. Now, we can write down g of x straight away, if you remember what we did last time. So, what is that? That is, you have to start with 1. See, 1 corresponds to this, right, and here this is a1, right, a1 equal to 1 here, right. So now we can use a1 equal to 1 here. So therefore this you can take 1 into x. Now here this is a2, a2 is minus 16, so therefore minus 16 x square, right, and this is a3, that's 20, so plus 20 x cube. This will be the 1 plus x plus minus 16 x square plus 20 x cube would be the generating function, right. Sorry, not this is the generating, this is not the generating function. I am saying that, see, g of x will be equal to some q of x by p of x, sorry, p of x by q of x, and this q of x will be this q of x, this is what will go to the denominator, because now when you do that procedure, g of x into this product will come, right. And on the other side, what will be there? So first h0, that is 0, so let us try to write it from here, h0, that is 0, plus then h1 plus h0 into a1, so anyway that is 0, that is just h1x, that is x. Next one is h2, which is minus 1, right, plus h1 into a1, this is 1, that is 1, right, and then h0 into a2, anyway h0 is 0, that will go away, this will be minus 1 plus 1 into x square, right, and this is again 0, because minus 1 plus 1 has become 0, so this is 0 times x square, right, and then there is nothing more, because from x cube onwards, third term onwards will disappear, right. So this will be just x, right, this is our p of x will be like this. So if you are confused, what I am doing is just substituted the values for h0 in this formula for p of x. I just substitute the values for h0, h1, h0, this one, right. So because k was equal to 3, I only have to go up to x square term, right, x cube term onwards will not be there. So that's how I got x there, right. So again, so if you remember how to do this thing, it's very easy, but even if you don't remember, you can go through the entire procedure and get p of x and q of x. So p of x is x here, q of x is equal to this here. So what do you get? G of x equal to p of x by q of x, which is equal to x divided by, right. So x divided by 1 plus x minus 16 x square plus 20 x cube. So now if you want to get a closed form for, if you want to get the value of hn, so we want to find the coefficient of x raised to n in the expansion of this. So we can again use the method of partial fractions. What we do is we write it as some c1 times, okay, first we should know how this will factorize, 1 plus x minus 16 x square plus 20 x cube. So with some effort you can show that this is 1 minus 2x whole square into 1 plus 5x, right. You should try it out, and then once you know this thing, you can write this is equal to some c1 times 1 minus 2x plus c2 times 1 minus 2x whole square plus c3 times 1 plus 5x. Now the same thing we did last time, right, equate the numerator is x here, right, numerator is x here, this with c1 times yeah, we will get x equal to c1 times, this is routine stuff, 1 minus 2x into 1 plus 5x plus c2 times 1 plus 5x plus c3 times 1 minus 2x whole square. Now equate the constant terms from both sides, and then the coefficient of x from both sides and coefficient of x square from both sides, and then we get 3 simultaneous equations, and solving it we can get the values of c1, c2, c3, and then we will be back to very familiar forms, so which we can use to infer the coefficient of x raised to n. So, we have to get the coefficient of x raised to n from this, we have to get the coefficient of x raised to n from this thing, and then we have to get the coefficient of x raised to n from this thing. We know how to, we already know the trick by which we can infer the coefficient of x. For instance, if you want to get the coefficient of x raised to n in C2 by 1 minus 2x square, what will you do? This will be equal to k equal to 0 to infinity, because this is minus 2, right. So, this is, remember, this is C2 into 1 minus 2x whole power minus 2. So, this is just write minus 2, choose k here, right, and then that is, this is x is minus 2x. So, minus 2x whole raised to k, right, and this we know, this is k equal to 0 to infinity, and you know how did we do this, k plus 2 minus 1, right, choose k. So, this is just k plus 1, choose k into, so this minus 2 raised to k. Okay, sorry, we also had a minus 1 raised to k coming from here, and we have minus 2 raised to k here, and that is x raised to k, and this minus will go away. We will just have k plus 1, choose k. So, this will look like k equal to 0 to infinity, this will be k plus 1, choose k is just k plus 1 into, and here minus 1 raised to k is there, minus 1 raised to k will come, minus 1 raised to 2k will disappear, and then just 2 raised to k will be there, right, into x raised to k, 2 raised to k into x raised to k. So, the coefficient of x raised to n which is coming from this will be just n plus 1 into 2 raised to n, right. Similarly, we can find that those other terms are easier. For instance, these terms are easier to handle. As once we know C1, C2, C3, we will easily able to, we will be right. So, we have this C2 here, right, okay, C2 into, right, we will be able to get the coefficient of x raised to n. So, the thing is that again something times 2 to the power n, something times right, finally the answer will look like this. So, you have to work it out yourself because you do not want to waste time on this. So, Hn is equal to minus 2 by 49. So, this is the first coefficient, this will correspond to C1, okay, into 2 raised to n plus 7 by 49 into, this will correspond to C2, n plus 1 into 2 raised to n minus 5 by 49 into minus 5 raised to n. This will correspond to C3, okay, this one. So, this is what we will get. But interesting thing is that if you stare at it, this is when we try to solve the recurrence relation, the linear homogeneous recurrence relations with constant coefficients, kth order, we have got solutions of similar form, some constant to the power n, some C1 to the power n, C2 to the power n, C3 to the power n, where they were the roots of the characteristic equation with some things like this along with it as multipliers. This is what we got there also. So, now we got some numbers here. So, we will tend to think that maybe these are the roots of the characteristic equation, but then we did not consider the characteristic equation here at all. So, is it possible that they are again the roots of the characteristic equation? We just briefly discussed this issue, right. So, what is the relation between the characteristic equation and this Qx? Because here these numbers, these 2 to the power n, 2 to the power n and minus 5 to the power n you see here, right. They actually are the roots of Q of x. Why? Because our g of x was written as p of x by q of x. Then when we considered the the method of partial fractions, we factorized q of x. So, the roots of q of x appeared. So, for instance, it was c1 by 1 minus 2x, one term. Another term was c3 by 1 minus 5x, right, and another term was c2 by 1 minus 2x square, right. So, here this 2 was right, it has something to do with the q of x. It is not the roots, but it has something to do with the q of x, right, because q of x could be written as, because this is like we could write q of x equal to 1 minus 2x whole square into 1 plus 5x. That is why those things came, and that's so that is the reason in the answer 2 to the power n and 2 to the power n and 5 to the minus 5 to the power n plus. So, minus 5 to the power n appeared, right. So, what is the relation between this Qx and the characteristic equation? What is the characteristic equation here? Characteristic equation, we will go back to the characteristic equation. It looked like, right, for instance, our recurrence relation was Hn plus Hn minus 1 minus 16 Hn minus 2 plus 20 Hn minus 3 equal to 0, right. So, the characteristic equation automatically, because this is, see, there will be x, if you multiply by x raised to n here, x raised to n, x raised to n, x raised to n, and we cancel off x raised to n minus 3 from everywhere. So, we will end up with this kind of a relation Hn, right, into right Hn into sorry, no, this was not the characteristic equation. So, sorry. So, our recurrence relation was Hn plus Hn minus 1 minus 16 Hn minus 2 plus 20 Hn minus 3 equal to 0. So, how do you find the characteristic equation? So, we find the characteristic equation by, so thinking that suppose Hn is of the form some x to the power n, some constant to the power n, we will consider it as a variable, right, some to find out that power. So, this will be x raised to n plus x raised to n minus 1 minus 16 into x raised to n minus 2 plus 20 into x raised to n minus 3 equal to 0. This is what we get. Now, we cancel off x raised to n minus 3 from everywhere. So, this will give an x, this will give an x square, and this will give an x cube, right. So, the characteristic equation is x cube plus x square minus 16x plus 20 equal to 0. This is the characteristic equation, right. Um, and we know that if at all the Hn has a solution of the form some constant to the power n, that constant should satisfy this characteristic equation x cube plus it should be a root of this characteristic equation, right. So, now let us say the characteristic equation has roots q1, q2, say q k, right. Then our characteristic equation r of x can be written as x minus q1 into x minus q2 into x minus qk, right, isn't it. So, this is the way we can write the characteristic equation. Now, on the other hand, if we had taken r of 1 by x, so put substitute x equal to 1 by x. So, for instance, you can substitute instead of x you can put 1 by x. So, you will get 1 by x minus q1 into 1 by x minus q2 and so on 1 by x minus qk. So, this will look like x raised to k into 1 minus q1 x plus 1 minus q2 x, right, and 1 minus qk x, right. But there is a relation between this and our q of x. So, what is the relation between this and the q of x, right? This q of x is actually, so you can see that q of x is actually the reverse of the characteristic. So, let us write r of x and q of x together. R of x is x raised to k into a1 x raised to k minus 1 plus a2 times x raised to k minus 2 plus ak times so that is ak, right. This is the way we write the characteristic equation. Okay. Now, on the other hand, qk looked like qx looked like this 1 plus a1x plus a2 x square plus finally here ak times x raised to k. So, there should be a relation between this and this because the coefficients are the same and just that this is x raised to k, here it is 1, here is x raised to k minus, here is x. So, we can with some inspection we can see that the relation is that q of x is equal to x raised to k into r of 1 by x, isn't it. If you put you just have to substitute 1 by x in this formula. So, that is 1 by x raised to k, you multiply by x raised to k, this will become 1, right. Similarly, here 1 by x raised to k minus 1 multiply x raised to k, you will get an x here and a1 left, like that. So, this is the relation between the two, right. So, qx is actually x raised to k into r of 1 by x. So, but we know r of 1 by x is actually, so we can substitute for let us see x raised to k into, so r of 1 by x we already sketched out here, r of 1 by x is this, right. So, sorry, r of 1 by x is, so this what happens is here 1 by 1 minus qx we have an x raised to k in the denominator, right. This is what r is. So, we can substitute it there x raised to k into 1 minus qx 1 minus q1x into 1 minus q2x. So, okay, we will do it in the next page. So, I will repeat it. So, this relation we can see See, this relation is easy to see once we write R of x and Q of x. This is the characteristic equation for a recurrence relation of the form Hn plus A1 Hn minus 1 plus A2 Hn minus 2 Hn plus A1 Hn minus 1 plus A2 Hn minus 2 and so on, Ak Hn minus k equal to 0. So, this is the recurrence relation, and now the characteristic equation for this thing was written here, this one, right, and Q of x for the recurrence relation was written here. Q of x in the sense g of x is equal to p of x by q of x, that particular q of x will come like this. And from this thing we notice that q of x is actually x raised to k into r of 1 by x. But actually the characteristic equation has roots, characteristic equation r of x equal to 0 has roots q1 to qk, say. Then r of x equal to x minus q1 into x minus q2 into so on x minus qk. So, then we can easily find out what is r of 1 by x, which is actually so we have a 1 by x raised to k coming in the denominator. We will get 1 minus q1 x into 1 minus q2 x and so on, 1 minus qk x. So, we are just putting, instead of x we are putting 1 by x. So, 1 by x, so taking a common denominator, it is 1 minus q1 x here by x. So, here 1 minus q2 x by x, here 1 minus qk x by x. So, that all those x's in the denominator will combine to form a 1 by x raised to k here. So, that is what it is, right. Now, here we can substitute x raised to k into 1 by r of x. So, when we substitute here this formula, right, that x raised to k and x raised to k will cancel, and we just get q of x equal to, we get q of x is equal to, right, 1 minus q1 x into 1 minus q2 x into 1 minus qk x. So, now it is not surprising at all that these are actually the roots of the characteristic equation. And you know, finally, when g of x is equal to p of x by q of x is converted into some form of this sort, it will look like this, right. So, suppose in the case that q1, q2 all of them were different, we will write the simplified form due to by the method of partial fractions like this, 1 minus q2 x and so on, right, ck by x. So, we will be finding the value of c1, c2, ck, and it is not at all surprising that q1 raised to n, q2 raised to n, qk raised to n, etc. appear in the final answer, right, because we know in the, when we use the binomial, generalized binomial theorem to expand it, this q1 raised to n, q2 raised to n, etc. will appear, right. That is why we see the roots of the characteristic equation again in the solution when we use the method of generating function also. We will continue in the next class.